Okay, guys, I wanted to go through this equation sheet with you and make sure, since I've changed it a little bit, I want to make sure that you can follow it easily. I want to make sure this is recording. Yes, it is. Okay. I can never find this thing. Okay. So remember, it kind of goes through things in the order that we had class. So we start out here with our sigmoid Emax model. This is our sigmoid Emax model. And of course, you can simplify that to the Emax model and the linear model as you see fit. This section here is all about bioavailability and bioequivalence. I don't think it needs any more explanation than that. Remember, here's where you can get your area under the curve for that tail section. I expect you to know how to do the trapezoidal rule. But if you need to know a constant, if all you have is one concentration and out to infinity, if this is your time concentration curve, you can figure out this area here by using your concentration over your K. And you can see that's repeated here. This is using a multi-compartmental, right? But if you just have one compartment, then this piece will do the trick for under the curve from 0 to infinity, if you know that. So this mirrors that. This is one of the only equations where it's not rearranged according to the dependent variable. This is the independent variable here, and these are the dependent variables in this situation. But I wanted you to see how we set, as long as this clearance remains constant, these two will be equal to each other, because these are just rearrangements of these two equations. Okay, good. I don't know if I can erase everything. Well, I don't need to. The next section is volume distribution and protein binding. This is an equation you will use quite a lot. And remember, I've given you these standards so that you can figure out the volume distribution of any person if you're given the right amount of information. This is an important equation. This is just our Michaelis-Menten that describes binding, the capacity and affinity of the system. Then we get into clearance. Remember, clearance for any organ is blood flow to that organ and the extraction efficiency. And then this is using the well-stirred jar model. And our intrinsic clearance, again, here's another Michaelis-Menten with capacity and affinity. We know that our extraction ratio is 1 minus E gives us our fraction that escapes that first pass effect through the liver, which can also be described by this. I've also given you that hepatic clearance is dependent upon Q for a high extraction drug, and intrinsic clearance for times fraction unbound for a low extraction drug. Our fraction that escapes the first pass effect is dependent upon Q over intrinsic clearance, because most of these drugs are non-restrictively cleared, as you remember, and our low E, pretty much all of it makes it through that first pass. I've also given you these standard blood flows to the kidneys, to the glomerulus, and to the liver. Here's another reminder of what restrictive clearance means. It's restricted to only free drug, and non-restrictive clearance sees all the drug as being free and available. If we get into renal clearance, remember, FE is a fraction of drug excreted unchanged in the urine. It's basically the percentage of clearance due to the kidneys, right? And we expect that 1 minus FE is hepatic clearance, right? So we can always figure out our renal clearance and our hepatic clearance if we know FE. We know that filtration clearance and tubular secretion clearance are adding drug to the nephron, to the urine, and then we take some back if the drug is reabsorbed in the distal tubule. Filtration clearance is GFR times fraction unbound. The efficiency of tubular secretion is, this is not, well, don't worry about this. This is what we want to focus on. This is our intrinsic clearance tubular secretion. Here's our number of tubular secretion sites, capacity, and affinity. Another Michaelis-Menten. Our renal function of our patient can be determined if we compare our patient, this means our patient, that little star or asterisk, compared to normal, which we usually use GFR to compare it to. And we can determine our patient's relative creatinine clearance can give us their renal function. And then we can use that to plug in here if we know the FE of the drug and we know the normal clearance of the drug, we can adjust it for renal failure. All right, so there's all clearance. Then as we move on, this is all multi-compartmental, right? Multi-compartmental, how we can use multi-compartmental, the macro constants, which are your y-intercepts, however many you have, and your slopes of your elimination lines for each of those compartments, right? Those are your macro constants. And your micro constants are the movement between compartments, right? So if this is compartment 1 and this is compartment 2, this is going to be K12, this is going to be K21, and then out of the first compartment is K10 to out of the body. You can determine volumes and different micro constants. Your micro constants can be determined by using macro constants and then using that. So you start out by figuring out K21 using the macro constants, and then you go do K10, because these are macro constants, and one micro constant, macro constant, micro constants. Okay, good. And then this last section is some TDM. So I did give you this loading dose equation, but you need to know half-life. You need to know K. You need to know CSS average. Right. You need to know the Cockcroft and Galt equation to be able to figure out creatinine clearance. This is an estimate, which is 140 minus age times their weight in kilograms. You need to know the rules for determining what the weight is, times 72 times their serum creatinine. And then this whole thing, you take 85% if you're talking about a woman. Okay? Need to know how to figure out ideal body weight.